Welcome back. Let's learn about multivariable functions. Alright, so far in math, through algebra, pre-calculus, Calc 1, Calc 2, and even Calc 3, we have pretty much exclusively worked with functions of a single independent variable, right? Functions that are defined using one independent variable that we typically represent with x, but we have used other variables in the past. However, there are many quantities, some of which you are familiar with, that are represented by functions of two or more independent variables. And we call these functions functions of several variables, or more simply, multivariable functions. They are functions that are defined with two or more independent variables. Okay, so for example, if you think about the volume of a cone, more specifically the volume of a right circular cone, we represent the volume with this formula. The volume is equal to pi r squared times h, where r is the radius and h is the height. This can be viewed as a multivariable function, in particular a function of two independent variables, those variables being the radius r and the height h. Depending on the value of the radius and the height, the output value for the volume will be different. Alright, the output of the volume depends on the values of those two independent variables. Or for another example, consider the volume of a rectangular solid, where volume is equal to L times W times H, where L is the length, W is the width, and H is the height. We could view the volume here as a function of three independent variables, those variables being the length L, the width W, and the height H. Depending on the value of each of those variables, the volume of the rectangular solid will change. The volume depends on the values of those independent variables. Okay, and of course these are just two examples of many different examples that we could pull from of multivariable functions in practicality. But we're not quite ready to look at the applications of multivariable functions at this point. We still have to fully introduce them here, and so let's begin by looking at notation. And we actually use a very similar notation to single variable functions for multivariable functions. When we have a function of a single variable, we represent it with f of x. X is the independent variable, so we put it inside those parentheses. Same thing with multivariable functions. We denote a multivariable function of two independent variables like this, f of x, comma, y. We put both of the independent variables, in this case x and y, inside the parentheses for the function. Now the way that I would actually read this is f of xy, or f of x and y, but just saying f of xy is going to be the easiest. Or if you have a function of three independent variables, the notation will look like this. You'll have all three of those independent variables, x, y, and z, separated by commas inside the parentheses for the function. And you would read this as f of x, y, z. Alright, now remember, functions are not just composed by independent variables, they also include a dependent variable. And so for example, when we had a function of a single variable, such as f of x equals x squared, another way that we could write that, using the dependent variable, which in this case would have been y, we could write the function as y equals x squared. Alright, we set the dependent variable equal to the function in terms of the independent variable. We can do a very similar thing for multivariable functions, except the dependent variable will look a little bit different. For example, let's say that we have a function of two variables, f of xy, that's equal to x squared plus y squared. In this case, the independent variables are x and y, so y will not be our dependent variable here, like it was for our single variable function. In this case, we will use a different letter. Typically, we use z. Z will be the dependent variable, so the way that we could rewrite this multivariable function would be z is equal to x squared plus y squared. We set the dependent variable equal to the function in terms of the two independent variables. Okay, or if we have a function of three independent variables, f of x, y, z is equal to x squared plus y squared plus z squared, we could also rewrite this function using a dependent variable, but we have to use a different variable once again, because now for this function, x, y, and z are independent variables. And typically for multivariable functions with three independent variables, we will use w as the dependent variable. So we could rewrite this as w is equal to x squared plus y squared plus z squared. All right, the dependent variable is equal to a function in terms of the three independent variables. Alright, so really, the notation for multivariable functions is not all that different from a function of a single variable. But it is important to realize that in each case, the independent variables will always be listed inside the parentheses for the function. So you can very quickly identify how many independent variables there are for your multivariable functions. Okay, so the number of independent variables can change, but what won't change is the number of dependent variables. There will still only be one dependent variable for all of these functions. Okay, so that's a nice little introduction to multivariable functions, but let's take a closer look. Let's compare and contrast multivariable functions to functions of a single variable, because just like functions of a single variable, multivariable functions also can be represented by graphs and have a domain and range for the independent and dependent variables. And so here's a nice chart to help us keep everything straight. In this column, we have our single variable function, y equals f of x. In this column, we have a function of two independent variables, z equals f of xy. And then in this column, we have a function of three independent variables, w equals f of xyz. For this single variable function, the independent variable is x. For this multivariable function, the independent variables are x and y. And for this multivariable function, the independent variables are x, y, and z. Once again, you can always identify those independent variables by looking inside the parentheses for your function notation. And then just as we got done discussing, the dependent variable in each case is y for the single variable function, z for a function of two independent variables, and w for a function of three independent variables. But now let's talk about the graphs. What do the graphs look like for each of these types of functions? Well, you should be pretty familiar with the graph of a single variable function. The graph of y equals f of x is represented in a two-dimensional plane. We have an axis for the independent variable x and an axis for the dependent variable y. And so what happens is you input different values of the independent variable x into the function to get out different output values of the dependent variable y. So you put in a value of x and you get out a corresponding y value. And so from that, you can get a collection of points for your function that then make up a curve. That's what we get from a single variable function. But for a function of two independent variables, we're no longer working with curves or lines. The graph of the function will be in three dimensions. You'll have an axis for each independent variable, x and y, and then you'll also have an axis for the dependent variable z. And so in this case, you input values of x and y into the function and get out an output of z. So all of your input values represent a point somewhere in the xy plane that then, when plugged into the function, corresponds to a height along the z-axis. And so from plugging in different values of x and y into the function and getting out a z value, you get different points within the 3D coordinate system that together make up a surface. Alright, so functions of two independent variables give you three-dimensional graphs of surfaces. But what about functions of three independent variables? Well, the graph of these types of functions will be in 4 dimensions, which we have no idea how to graph, which is why I have a question mark here. I have no way of showing you what that looks like, but if we could actually graph in 4 dimensions, we would have an axis for each of the independent variables, x, y, and z, as well as an axis for the dependent variable w. And you would be able to form some type of 4-dimensional shape by plugging in different values of x, y, and z together into the function and getting out one output for w to get a 4-dimensional point, I guess. And all of those 4-dimensional points together would form some type of 4-dimensional shape. Again, we don't know what that looks like, but the same type of process is going on here that happens when we graph single variable functions and functions of two independent variables. Okay, so those are the graphs of each of those types of functions, but what about the domains? What do the graphs of the domains look like for each type of function? Well, remember, the domain corresponds to the independent variable. The domain represents the set of possible input values for your function. So for a single variable function, which only has one independent variable, you would graph the domain in one dimension for one independent variable. Looking at this graph here and thinking about the domain, the different possible values of x that can be input into the function would be values of x towards infinity, but not including 0, because this line is not touching the y-axis, or where x equals 0. It's getting close, but it won't really touch that. So we would represent that domain like this. We have our number line representing our different values of x, and we have that open parenthesis at 0, or you could draw an open circle at that point, and then an arrow pointing in the positive x direction. All right, so this would represent all the different values of x that are possible inputs for this function. Now, for a function of two independent variables, the domain will no longer be in one dimension, but two dimensions because we have two independent variables. We have to account for the different input values of both x and y. And so the domain will be plotted in the xy plane. It will represent all the different combinations of x and y that can be plugged into the function and get out a corresponding z value or height. All right, so looking at this surface here, clearly the domain, or the different possible input values of x and y, will be limited to the points within this circle. All right, any coordinates of x and y within this circle can be plugged into this function to get a corresponding z value. All right, anything outside of that circle, as you can see in this graph, does not result in a point that is part of this surface. Okay, and then for our function of three independent variables, the domain would actually be represented in 3 dimensions. You need to take into account all 3 of the independent variables. And so an example of what a domain might look like for a 4-dimensional surface or shape represented by this function would be a sphere. Within this sphere in 3 dimensions would be a set of values for x, y, and z that could be plugged into the function that will result in a value of w, and then all those different values of w from those different sets of points would form a 4-dimensional shape. All right, so that's what the graph of the domain will look like for each of these types of functions. But the main points you want to take away here are this. Firstly, the graph of the function will have 1 dimension more than the number of independent variables, right? A function of a single variable had a 2-dimensional graph. A function of 2 independent variables had a 3-dimensional graph, and a function of 3 independent variables would have a 4-dimensional graph. So the graph of the function will always have 1 more dimension than the number of independent variables. And you also want to remember that the domain of a function will have the same number of dimensions as the number of independent variables. All right, a single variable function has a domain in 1 dimension. A function of 2 independent variables has a domain of 2 dimensions, and a function of 3 independent variables has a domain of 3 dimensions. Okay, in other words, as I've already mentioned, you'll need an axis for each independent variable. Okay, and we're going to come back to the domain of multivariable functions later in this lesson. That's how we're going to end, by looking at how to find the domain of a multivariable function. But first, there's a couple things about multivariable functions that you need to be aware of. And the first thing is regarding the definition of multivariable functions. Just like single variable functions, multivariable functions, whether it's f of xy or f of xyz, they require that each input of xy or xyz corresponds to a unique value for the dependent variable, or a single output. All right, and so what do I mean by that? Well, consider this. You should be familiar with this equation from earlier in Calculus 3. We know that x squared plus y squared plus z squared equals 9 represents a sphere in the 3D coordinate system, specifically a sphere with a radius of 3, because x squared plus y squared plus z squared is equal to the radius squared, and the square root of 9 is 3. But we cannot say that for this equation of this surface, that z would be a function of x and y, because there are inputs for x and y that result in multiple values for z. And so, for example, if you consider the x and y values of 0 and 0, that would be at the origin of the xy plane, those 2 coordinates of 0, 0 for x and y correspond to 2 different points on this sphere. Right? They correspond to this point up here, where the z coordinate is 3, and it also corresponds to this point down here, where the z coordinate is -3. In other words, there are 2 different outputs for a single input of 0, 0 for x and y. 0, 0 results in z equal to plus or minus 3, the points at the top and bottom of the sphere. And so what that means is that this entire sphere could not be represented by a single multivariable function. Okay, because just like single variable functions, a multivariable function requires that each input only corresponds to a single output. If there are 2 outputs for 1 input, that is not a function. And so the way that we would get around that is by representing this sphere with two different multivariable functions. And so here's what that looks like. What we would want to do is solve for z in this equation. And to do that, we would need to subtract x squared and y squared from both sides of the equation. So that would give us this. We would have z squared is equal to 9 minus x squared minus y squared. And then to finish solving for z, you would need to take the square root of both sides of the equation. So you would get z is equal to the square root of 9 minus x squared minus y squared. Or really what you'd get here is z equals plus or minus the square root of that expression. Okay, we would split that up into two functions. You would have z equals the square root of 9 minus x squared minus y squared, and z equals the negative square root of 9 minus x squared minus y squared. Okay, you'd get these two different functions that together would represent the entire sphere. This equation, the positive one, would represent the top half of the sphere, or the part of the sphere above the xy plane, and then this equation where you have the negative in front of the square root, that would represent the bottom half of the sphere, or the part of the sphere below the xy plane. Okay, so really it's the same idea with how we treated circles with single variable functions. A circle is not a single variable function because there would be multiple outputs for y that correspond to a value of x, right? If you think about x equals 1 for whatever this circle would be, that value of x corresponds to this y coordinate and this y coordinate, so the entire circle would not be a function of a single variable. All right, that's where we get that idea of the vertical line test. If you can draw a vertical line through your curve and hit the curve twice, like we would for this circle many times, then that curve, or in this case the circle, is not a function. All right, that's the same idea that we are applying here for multivariable functions, but of course we're now working with surfaces rather than curves. Okay, so it's the same idea, but just extended to another dimension. All right, but assuming that you can represent a surface with a multivariable function, you can plug in any set of values for the independent variables on the domain and get back one value for the dependent variable. And so let's take a quick look at how we evaluate multivariable functions. Here I have an example where we want to evaluate these different functions. Now we're going to start with a single variable function, just to sort of review what we're doing here. But if we have a function f of x equals x squared, and we want to evaluate it at x equals 4, what we do is we plug 4 in for x in the function. All right, so we would get f of 4 is equal to x squared, which would be 4 squared, which is equal to 16. All right, so that's how we evaluated a single variable function. But what if we have a function of two independent variables? In this case, f of xy equals x times y. Specifically, we want to evaluate it at 3, negative 2. What this means is 3 is the value of x and negative 2 is the value of y. That's what we are going to plug in to this multivariable function. It will look like this. We'll have f of 3, negative 2. All right, we're plugging in those two values for x and y in the multivariable function. And that will be equal to x times y, where x is 3 and y is negative 2. So we'll have 3 times negative 2 equals negative 6. All right, so really it's not all that different from plugging values into a single variable function. The only difference is that there's a second value or a second independent variable to take into account. Just make sure you plug in the right numbers for the right variables based on how they are listed. All right, and so for our last example here, we have a function with 3 independent variables. F of x, y, z is equal to x plus y divided by z, and we want to evaluate it at this ordered triple, 6, 9, negative 3. So 6 is the x value, 9 is the y value, and negative 3 is the z value. So make sure to put those into the right places in the function. All right, so we'll have f of 6, 9, negative 3, and that will be equal to x plus y. So we'll have 6 plus 9 in the numerator, so 6 plus 9, and we're dividing by z, which is negative 3. So we'll write down negative 3. Then 6 plus 9 is 15, divided by negative 3 is negative 5. So we get negative 5 as the value on that function for that particular set of values for x, y, and z. Okay, so really not too bad. Evaluating multivariable functions is very similar to evaluating a single variable function. Now, something else that you need to know about multivariable functions is that just like with single variable functions, you can create combinations of multivariable functions. right? If you recall from pre-calculus, or sometimes you learn this in algebra, but you can combine two functions f of x and g of x using the different operations of addition, subtraction, multiplication, and division. Remember that a function f plus g of x is equal to the addition of those two functions, f and g. Same thing for subtraction. F minus g of x is equal to f of x minus g of x. You can also multiply two functions. F times g of x is equal to f of x times g of x. And then for division, f divided by g of x is equal to f of x divided by g of x, provided that g of x, of course, is not 0, because then this would be undefined. All right, but you can add, subtract, multiply, and divide functions to create a new function with single variable functions. And you can do the same exact thing for multivariable functions. You can add two multivariable functions, f and g, and create a new multivariable function, f plus g of xy, right? You can add f of xy and g of xy. You can also subtract them to create a new equation. You can also multiply them, and you can also divide them to create a new function, provided that the bottom function is not 0. All right, g of xy cannot be 0, otherwise this would be undefined. All right, we're not going to look at any examples of this in this video. I'll have some examples in the examples video for this topic of combining multivariable functions, but I think it's a fairly straightforward idea. You are allowed to add, subtract, multiply, and divide multivariable functions, assuming that they have the same number of independent variables. But something that is a little bit different is composite functions. Unlike with single variable functions, you will not be able to form the composite of two multivariable functions. In other words, you will not be able to plug a multivariable function into another multivariable function. Instead, what you can do is create a composite function where the function you're plugging into, f, is a single variable function. All right, now what do I mean by that? Well, first of all, remember that this is what a composite function is. For two functions, f of x and g of x, these are single variable functions. You can take the composite of those two functions by plugging g of x into f of x. You can't really do this for two multivariable functions. Instead, this is what you can do. F will still be f of x, a single variable function, but now g will be a multivariable function, g of xy. You can take the composite f of g of xy by plugging that multivariable function of g into the single variable function. All right, you would replace each x in the function with this multivariable function. All right, so hopefully you can see if we didn't have f of x here, but rather f of xy, it's a little confusing on what you would do if you wanted to take the composite of these two functions. Where do you plug g of xy into this function? Do you plug it in for x? Do you plug it in for y? I suppose you could plug it in for both x and y, but that's not really the type of composite function we're talking about here, okay? So it just doesn't make sense for two multivariable functions, but it does make sense if you have one single variable function and one multivariable function, like we have right here. Okay, now let's talk a little bit more about the domain as well as the range of multivariable functions. Specifically, how do we find the domain and range of a multivariable function? And well, the good news is it's not all that different from how we did it for single variable functions. But before I show you, as a quick review, remember that the domain of a function is a set of all possible input values, meaning the possible values for the independent variables, and the range is a set of all possible output values, or the possible values for the dependent variable. Okay, you typically thought of domain as being the values of x and range being the values of y. You have to sort of alter your thinking about that here, because now with multivariable functions, y can also be an independent variable, and your dependent variable will be z, or if you have three independent variables, the dependent variable will be w. Okay, so you have to change your thinking about that a little bit, but otherwise, everything is pretty much the same. When you want to determine the domain of a multivariable function, such as f of xy equals x squared plus y squared, you want to be thinking about, are there any values for the independent variables that when I plug them in causes a problem? So this would be things like having a denominator of 0, or having a negative number underneath a square root or inside a logarithm. Things like that. You still want to be on the lookout for the same things. And so thinking about that for this function, well, there's no restrictions, right? You can plug anything in for x and anything in for y. You're just going to be squaring those values and adding them together. So really the domain here, or the set of all possible input values for the independent variables, will be everything, all real numbers. Okay, so there's no restrictions here. And so here's how we will write out the domain. You may be really used to using interval notation for your single variable functions, but unfortunately, interval notation is not as helpful for multivariable functions because it's hard to clearly distinguish the two independent variables, in this case, x and y. So what we do instead is use set notation, which maybe you haven't used for a little while, but that's okay. We use set notation here because it clearly shows the two independent variables and what the possible values are for each of them. All right, we'll write it like this. We'll say that the domain is represented by the set of all points x, comma y, such that, that's what this bar means, it means such that x belongs to the set of all real numbers and y belongs to the set of all real numbers. Okay, if you haven't seen this notation before, or maybe it's been a while, this little curved e is the Greek letter epsilon, and it just means that whatever is before it belongs to the set that comes after it. And this fancy R represents the set of all real numbers. All right, this is how we represent the domain for a multivariable function, particularly the case where any value of x or y will do. Now, there is another way that you could write this. Instead of writing out x and y individually here, you could also write the domain like this. You could say that the domain is a set of all values x, y, such that x, y belongs to r squared. And what r squared is not just the set of all real numbers, but rather the set of all ordered pairs of real numbers. All right, in other words, it's all the points in a plane. That's what r squared represents. So this is a little more compact or easier way to write the same domain, but it's ultimately up to you how you want to write it. Okay, so I would probably go with this one because it's a little bit easier to write, but if you prefer this way, that's fine too. Okay, so that's the domain for our multivariable function, but what about the range? What is the set of all possible output values, or the possible values for the dependent variable of this function, which in this case we would say is z. Since it's a function of two independent variables, you could rewrite this as z is equal to x squared plus y squared. What would be the possible values of z here? Well, remember, we can plug in anything we'd like for x and y. There are no restrictions. The domain is all real numbers for both x and y. But both x and y are being squared here, so even if you put in a negative number for x or y, they are going to be squared to be made positive, and then you're adding those two numbers together. So there's no possible way that the output here will be negative. But other than that, we can get any value for z. All right, so just by looking at the function here, we can see that all of the outputs will be positive. So that means that the range will be all positive values for z, including 0 because x and y could be 0, and 0 squared plus 0 squared is 0. Okay, so here's how we'd write that. The range is represented by the set of all values of z such that z is greater than or equal to 0. All right, all values greater than or equal to 0 are positive values of z. Now, if you wanted to, I guess you could use interval notation for the range of your dependent variable, but since we use set notation for the domain, I like to use it for the range as well. All right, so that's my final answer here. This would be the range for our multivariable function right here. Okay, and this answer for our domain should make sense, because if you remember back to the beginning of this lesson, we said that for a function with two independent variables, the domain will be in two dimensions, one dimension for each of those independent variables, and that's exactly what we have here. The domain only accounts for two independent variables, and we're looking at all values of x and y contained within r squared, which is the plane containing all ordered pairs of real numbers. All right, it's in two dimensions. So this function would represent a surface or a 3D graph, but its domain is in 2D. Okay, let's take a look at some more examples of determining the domain and range of multivariable functions. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful, then I'd like to invite you to join my membership site, JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. So if you are interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. Next up, we have the function g of xy is equal to 2xy divided by x minus y. Alright, now first of all, this is a multivariable function of two independent variables, so this does represent a surface in 3 dimensions, and the domain refers to the values of x and y, which will be in 2 dimensions. But what you want to look for here are any values of x or y that are going to result in an undefined value. And if you look at this function here, it is a rational function. We have some expression divided by another, and so that denominator cannot be 0, because if it is 0, you are dividing by 0, and that's an undefined value. All right, so what you want to do is set that denominator equal to 0, or really what you want to do is write x minus y does not equal 0, right? We do not want that denominator to be equal to 0. And so what values of x and y are going to make that happen? Well, if we just add y to the other side of the equation, you can see that x cannot be equal to y, which makes sense. If x equals y, then you'll have that number minus itself, which would be 0. So that denominator would be 0 and cause a problem because you can't divide by 0. And so this is clearly the restriction we have for the domain of this function. So here's how we'd write that out. The domain of this function would be the set of all values of x and y such that x does not equal y. That's it. Everything else is valid. You can plug in anything you'd like for x and y. The numerator is going to be fine, and the denominator is going to be fine as long as x does not equal y. Okay, so that's the domain. But now what about the range? What are the possible output values for z? Because x and y are the independent variables, which means that our dependent variable would be z. You could rewrite this to be z equals this function. And looking at what we have here, we could get anything. There's no squares in this expression, which would limit us to positive outputs, right? It's not x squared, y squared in the top here, and there's no x squared and y squared in the denominator. It's just xy and x minus y. And so any value of z is going to be possible here. The range would just be the set of all values of z such that z belongs to the real numbers. Okay? You could also write it like this. You could say it's from negative infinity to infinity, or just write all real numbers. It doesn't matter. That would be the range for this multivariable function. Next up, we have this multivariable function. H of xy is equal to the square root of 9 minus x squared minus y squared. Once again, we do have two independent variables, so this does represent a surface in 3D with a domain in 2D. And if we want to determine the domain, notice that we do have a square root here, and you cannot take the square root of a negative number. That will give you an imaginary number, which we are not working with here. We are only interested in real numbers. So what you want to do is set the inside of the square root to be greater than or equal to 0, because it could be equal to 0. The square root of 0 is fine. That's just equal to 0. So we'll have 9 minus x squared minus y squared greater than or equal to 0. All right, now we can make that a little bit nicer. If you add x squared and y squared to both sides of the equation, you'll get 9 greater than or equal to x squared plus y squared. Or really the way that I would write that is by flipping the two sides. So we would have x squared plus y squared must be less than or equal to 9. All right, so this would be our restriction for the domain. We can use any values of x and y as long as the sum of their squares is less than or equal to 9. All right, so we would write that like this. The domain is the set of all values x, y such that x squared plus y squared is less than or equal to 9. All right, that would be the domain for this multivariable function. But what about the range? Well, if you think about it logically, if the sum of x squared plus y squared has to be less than or equal to 9, then that means the biggest number you're going to be subtracting from 9 underneath this square root will be 9. So you'll get 9 minus 9, which would be 0. And so you'd have the square root of 0, which would have to be the smallest value, right? You're not going to output any negative values for this function because you're taking the square root of a value which will always output a positive value. So for sure we know one thing. We know that for the range, the values of z must be greater than or equal to 0. We know that the smallest value of z will be 0. But is there an upper bound? Is there a value that z cannot be bigger than? Well, actually, yes, there is. You might be tempted to say that z can be anything bigger than 0, but there is actually an upper bound or an upper limit to the value of z. Because if you think about it, x squared plus y squared, that is always going to be positive, right? It's always greater than or equal to 0. We could have added that in for our domain here. We're looking at values of x and y such that the sum of their squares is between 0 and 9. Technically, we could have added that in there. It's not necessary, but it is true. But what this tells us is that the smallest value that we could be subtracting from 9 underneath the square root is 0. We're not going to get anything smaller than that. You're not going to be subtracting any negative numbers because x squared plus y squared will be a positive value. So 9 minus 0 would be 9, and the square root of 9 is 3. That is the biggest possible value that you could get for z on this multivariable function. All right, so we know that z has to be between 0 and 3. Okay, I hope that makes sense. Each of these two bounds for z correspond to the upper and lower bounds of our input values. The biggest value that can result from our input of x and y is 9, and 9 minus 9 is 0. So the square root of 0 is 0. That's your lower bound. And then the smallest value that can result from our inputs of x and y would be 0. And so 9 minus 0 is 9, and the square root of 9 is 3. That would be your biggest value for z. Okay, so that would be the range of this multivariable function. And so now we're done. We have now found both the domain and the range. And so hopefully these last few examples gave you a good feel for how we find the domain and range of a multivariable function. But now I want to focus a little bit more on the domain, specifically how do we graph the domain for a multivariable function. This is something that can be helpful from time to time, especially later on in Calculus 3, so you do want to become familiar with graphing the domain of a multivariable function. And remember what we talked about earlier at the beginning of this lesson, that when you graph the domain of any function, you need an axis for each independent variable. Okay, so back to a single variable function for a second. If we have f of x is equal to 1 divided by the square root of x minus 1, the domain would just be for the values of x that can be input into the function. And so looking at this here, the denominator, you have the square root of x minus 1. There's a couple things that you have to be aware of here. For one thing, the denominator cannot be 0. So this inside of the square root cannot be 0. And it also has to be positive, right? X minus 1 has to be positive so that you're not taking the square root of a negative number. So what you would set up here is x minus 1 has to be greater than 0. It can't be equal to 0, and it has to be positive. And so from that, you would find that x needs to be bigger than 1, or x will be greater than 1 is the domain of this function. All right, and there's only one independent variable. So if we're going to graph this domain, we just need one axis, an axis for x. Okay, so here's our axis. This will be the x-axis. The domain is all values of x bigger than 1. So if I label this right here as x equals 1, you could graph the domain by drawing an open circle at that value and then pointing an arrow in the positive x direction. Okay, some people like to draw an open bracket there instead. It's really up to you, but that's how you would graph the domain of 1 to infinity, which is the domain in this case for this single variable function. But this is nothing new. How do we do this for a multivariable function? If we take a look at this function here, f of xy, it's equal to 2x plus 3y divided by x squared minus y squared. For this function, the numerator is fine. You can plug anything you'd like in for x and y. But in the denominator, we can't have 0. All right, x squared minus y squared cannot be equal to 0. So if we write that down here, x squared minus y squared cannot be equal to 0. And so if you add y squared to both sides of the equation, this is what would be true here. Y squared cannot be equal to x squared, which really means that y can't be equal to x, right? You could take the square root of both sides of the equation, and y cannot be equal to x, but really that would be plus or minus x. I suppose you could do it the other way around. You could say that x can't be equal to plus or minus y, but I like to write it this way because it's easier when we go to graph our domain. We're more used to working with equations of y equals something in terms of x, okay? Because remember, this is a multivariable function with two independent variables, so when we graph the domain, we're going to need an axis for each of those independent variables, which means we'll have two axes, and so we're in two dimensions, okay? So here's our 2D coordinate system, or our xy plane. This is the y-axis, and this is the x-axis. The domain that we found here is the set of all points xy such that y is not equal to plus or minus x. All right, and you could write it like that, or you could write it like this. Y cannot be equal to x, and y cannot be equal to negative x. I'll write it like that, because technically you would get two equations from this, or two different statements involving that does not equal sign. But if we're going to graph that domain, what we're saying is that we can use any values of x and y as long as y doesn't equal x and y doesn't equal negative x, which we could represent with two lines, right? We can graph y equals x and y equals negative x and just not include those lines in the domain. So here's how I do that. Y equals x is just a line that cuts through the origin of the xy plane that has a slope of 1, right? This would be y equals x. I'm drawing it as a dotted line because we're not going to be including it in the domain. And then y equals negative x would just be the opposite of that. It's a line that cuts through the origin with a slope of -1. All right, that's y equals negative x. And so then, to finalize the graph of the domain, I just like to shade in all the points that would be included, which is everything that is not these two lines. And so I would shade it in like this, just shade in the little triangular areas here. And I just like to leave a little space between the line and the shaded region to really indicate that we're not including those two lines where we have points that y equals x and y equals negative x. Okay, so that's how I would represent the domain here. I suppose you could shade in the whole coordinate plane, and then since you have those dotted lines, that means that those points are not included. But I do like to really emphasize the fact that we're not including those points, so I tend not to overlap the shading. Okay, but when you graph your domains in two dimensions, typically what you want to do is shade in all of the points that are included in that domain. And this domain here does make sense. If you were to actually look at this surface, and I'll provide a 3D render for you here, and you look at that surface from the top down, so that you're looking at the xy plane, you can see that any points where y equals x or y equals negative x are not included. Those values of x and y do not correspond to any values of z on the surface. All right, the surface is only formed by values of x and y within the domain, those four different triangular regions. Okay, so hopefully that helps you with the visual aspect of what we're doing here with the domain. But that's it for this example or this demonstration. Let's take a look at another example. Here we want to find and graph the domain of this multivariable function. We have f of xy is equal to the natural log of y minus x divided by the square root of x minus y plus 2. All right, so once again, this is a multivariable function with two independent variables. So it does represent a three-dimensional surface with a two-dimensional domain. So now let's first figure out the domain here. Are there any restrictions on x and y? Well, yeah, there's going to be some restrictions here because not only do we have a denominator that cannot be equal to 0, we also have a natural log function in the numerator where the input has to be positive, right? You can't input a negative number into a logarithmic function. So we have a couple things to keep in mind here. Let's start with the logarithm. Y minus x has to be greater than 0, okay? Because the natural log of 0 is undefined, as well as for any negative numbers. So we're going to have y minus x is greater than 0, and so if you add x to both sides, you'll have y is greater than x. That is one condition, or one restriction that we must have for this multivariable function. Y must be bigger than x. And then let's work on the denominator here. This cannot be equal to 0, and you cannot have a negative number because you can't take the square root of a negative value, okay? So that inside part of the square root here, x minus y plus 2, that needs to be greater than 0 as well. It cannot equal 0 because you have 0 in the denominator, and it has to be positive, so you're taking the square root of a positive value. Okay, now once again, just like with our previous example, to help you graph the domain, I like to write the different restrictions as a statement of y in terms of x. Okay, it's just going to make the domain easier to graph. So in this case, adding y to both sides of the equation, you'll get x plus 2 is greater than y. but then I'm going to flip the sides so it looks like this. We'll have y is less than x plus 2. And so now we have our two restrictions here. The way I would write the domain is like this. The domain is the set of all points x comma y such that y is greater than x and y is less than x plus 2. Okay, so that's the domain here. But now let's graph it. What does this actually look like as a graph? And so remember, it will be in 2 dimensions. So we need a y-axis and an x-axis. And our two restrictions are y must be greater than x and y must be less than x plus 2. So if you remember how to graph inequalities, this should be a pretty straightforward process. Y must be greater than x. That's based on the equation y equals x, but y must be bigger than x. So if we graph y equals x, but again, it's going to be a dotted line because we're not including y equals x, right? This is not y greater than or equal to x, it's just y greater than x. So this would be y equals x. And the inequality says that we're looking at all values of y greater than x. So that means we would shade in the region above that line. But I'm not going to do that quite yet. Let's also graph this inequality. Y is less than x plus 2. If you graph that line, y equals x plus 2, again, it will be a dotted line because we're not including x plus 2. We're just looking at y less than that value. That would also be a line like y equals x, but the y-intercept is at 2. So if this is y equals 1 and this is y equals 2, our line would look something like this. All right, that would be y equals x plus 2. And what this inequality is saying is y must be less than x plus 2. So that would be the region below this line. So what we're looking at here for the domain are the values of x and y between these two lines, right? Y greater than x is the region above this line, and y less than x plus 2 is the region below this line. So the shared space, or the overlapping of those two inequalities, is this region right in here. So you want to shade that in. That would be the domain of this function. Okay, any coordinates of x and y within this region are able to be plugged into this function and get an output for z. And once again, here's a 3D render of this multivariable function. You can see for that surface, if you were to look from the top down, that the points within the xy plane that give you outputs of z are in that region. There is a thin strip within the xy plane where the domain is contained. Okay, let's take a look at one more example of finding and graphing the domain of a multivariable function. All right, so for this multivariable function, we have f of xyz is equal to the square root of 25 minus x squared minus y squared minus z squared. Okay, so this is a little bit different than our previous examples because this is a multivariable function with 3 independent variables, meaning that it would be graphed in 4 dimensions. So there's no way that I can show you what that looks like. We don't really know how to graph in 4 dimensions. It just doesn't make sense to us in a 3-dimensional world. But we can still graph the domain because the domain will be in 3 dimensions, 1 dimension less than the actual graph of the function. Okay, we'll have an axis for each independent variable x, y, and z, which translates to 3 dimensions. And so thinking about the domain of this function, we do have a square root, so whatever's underneath that square root does need to be bigger than 0 or equal to 0 in this case. This is not in a denominator, so it can be equal to 0. You can have the square root of 0 and that's fine. But 25 minus x squared minus y squared minus z squared must be greater than or equal to 0. All right, and so adding x squared, y squared, and z squared to both sides of the equation, you get this: x squared plus y squared plus z squared must be less than or equal to 25. That's what this results in. And hopefully you recognize this to be a sphere, right? If you ignore this inequality for a second, if it was an equal sign, that would be the equation of a sphere. X squared plus y squared plus z squared equals a radius squared. In this case, 5 squared is 25, so the radius would be 5. That's what we're looking at here. The domain of this multivariable function, which by the way, would include all 3 of those independent variables. So you're looking at the set of x, y, z, such that x squared plus y squared plus z squared is less than or equal to 25. Okay, that would be the domain using set notation here. But let's actually graph it. It's just going to be all the points contained within a sphere. Here's what that looks like. This would be the z-axis, the y-axis, and then the x-axis. And then what we have just found for the domain is that it's going to be all the points contained within a sphere. And I say contained within because x squared plus y squared plus z squared is less than or equal to 25. All right, you're looking at all the values where the sum of these squares is less than or equal to 25, or the radius squared. So we're only working with x, y, and z values smaller than that radius of 5. Okay, you're going to be inside the sphere. So this doesn't have to be a perfect sketch. I'm just going to draw my sphere like this. The most important thing to write down here is that it comes out to a value of 5 in each direction. Okay, so you can label that and shade in that surface, but that will represent the domain of this multivariable function. That's really all there is to the graph. Whatever four-dimensional shape that this function represents, all the input values for x, y, and z that result in some four-dimensional output value, they're contained within this sphere. Okay, so this was the last example for this video involving the domain of a multivariable function. But to close out this lesson, I want to talk about one more thing regarding multivariable functions. And that is how to graph multivariable functions, which is actually something that we've sort of already done previously in Calculus 3. So I'm not going to spend a whole lot of time on this, and you'll see why in just a second. But the general process for graphing multivariable functions is this. For a function f of xy, which represents a surface, by the way, a three-dimensional surface, the first thing you want to do is just write it using the dependent variable, so set f of xy equal to z, and then you want to try to see if you can get that function or that equation in a form of a surface that you recognize. So this could be a plane, a cylinder, or a quadric surface, right? Those are three things you've already learned how to graph in previous lessons of Calculus 3. So I'm not going to go over those processes again here. If you want to review how to graph planes, cylinders, and quadric surfaces, feel free to go back to those videos, but I'm not going to repeat myself here. Okay, so if you can get that equation in a form of a surface that you recognize how to graph, then do so. But if you can't, if it's just a very complicated multivariable function that you can't identify to be any type of special surface, don't even bother trying to graph it by hand. You want to use a 3D graphing calculator of some kind. There's a lot of different ones online that are pretty good, but you can also get a handheld graphing calculator that does 3D graphs as well. Okay, and then a little note here. Obviously, if there are more than two independent variables, meaning that you have 3 or 4, you're going to have a graph that's in a higher dimension than 3 dimensions, which means you can't graph it, okay? We can't graph 4-dimensional shapes. We have no idea how to do that, let alone 5 dimensions or 6 dimensions, whatever. We can't graph anything above 3 dimensions, so don't bother. You can only graph multivariable functions that deal with 2 independent variables. Okay, so this is the process I would use, but really there's nothing new here. You've already seen how to graph planes, cylinders, and quadric surfaces, so I'm not going to show you any examples in this video. Now, there is actually another way to graph or visualize multivariable functions, but I'm going to leave that for the next lesson. Okay, so that is it for this lesson on the introduction to multivariable functions. If you do want to get some practice working with multivariable functions and finding their domain and range, feel free to check out the examples video for this topic that I'll have linked here on the screen. If you have any questions, please let me know in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.